Hey kids, welcome to section 6.9, using logarithms to solve exponential problems. Today we're going to learn how to use logarithms to solve problems involving exponential growth and decay, and how to use logarithms to solve problems involving logistic growth. So first, let's talk about exponential growth and decay. We talked a little bit about it back in section 6.1. The only thing that's different now is that we're going to talk about continuously increasing and continuously decreasing as our growth rate. So we have f of t equals a e to the kt, and we have f of t equals a e to the negative kt. Notice that we have a difference in the exponent based on if it's growth or decay. A is the initial amount that is there at the beginning, t is measured in time, and k is a constant that represents the growth and decay. We also have continuous compounding money. So we have a equals pe to the rt that we talked about in the last section. And we can also talk about exponential growth and decay with population, y equals ae to the kt power. So we're going to use these equations today to solve some word problems. So example number 1, the half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. The half-life of plutonium-239 is 24,000 years. Determine the value of K and round to the nearest thousandth. Well, since we have something decaying, we can use y equals ae to the negative kt power. Since I have something that is taking 24,000 years to get half of, well, if I'm starting with a, then half of a could be 0.5a equals ae to the negative k. And I don't know... I do know that t is 24,000 years. So if I divide both sides by a, I get 0.5 equals e to the negative 24,000 k. Well, I can get to the exponent by taking the natural log of both sides. So ln 0.5 equals ln e to the negative 24,000 k. The left side doesn't change, but the right side, the ln and the e go away, and you have negative 24,000 k. I can divide by negative 24,000. And that gives me k equals 2.888. So for part B, determine the equation of decay for plutonium-239. I'm going to leave the y alone. I'm going to leave the a, e. Now I'm going to put in the exponent negative k, which is 2.888, and then t. And then I can use that equation if I now want to figure out how much plutonium is left after a certain number of years, or how long it would take for a certain amount to be there. All right, here's an example number 2. The population P in thousands of a city can be modeled by the equation P equals 80 e to the 0.015 t, where t is the time in years. In how many years will the population of the city be 120,000? Well, the population is P, so 120,000 is P. So I have 120,000 equals 80 e to the 0.015 t. I can divide both sides by 80. So I get 1,500 equals e to the 0.015 t. I can get to the exponent by taking the natural log of both sides. The left side doesn't change, ln of 1,500. The right side, the ln and the e cancel, and so I'm left with 0.015 t. I can divide both sides by 0.015. And I get t equals 488 years. So after 488 years, there will be 120,000 people. All right, let's take a look at example 3. How many days will it take a culture of bacteria to increase from 2,000 to 50,000? Use k equals 0.657, round to the nearest tenth of a year. Well, this is population, so y equals ae to the kt power. The y is my ending amount, that's going to be 50,000. A is my starting amount, that's going to be 2,000, and I'm trying to find t. So 50,000 equals 2,000. K is 0.657 t. So I can divide both sides by 2,000. 50,000 divided by 2,000 is 25, equals e to the 0.657 t. I can take the natural log of both sides to get rid of the e. So the left side stays ln 25, but the right side becomes 0.657 t. Divide both sides by 0.657. T equals, actually, I think this is supposed to be days. So this would be nearest tenth, so 4.9 days. All right, if we look at number 4, this is called a logistic function. It looks like this function right here. So the population of a certain tropical island can be modeled by the function P of t equals 105,000 over 1 plus 2.7 e to the negative 0.0981 t, where t is the number of years since 1990. What is the maximum population of the island? Well, the maximum population is going to be like your asymptote of the function. And if I were to graph this logistic function, the asymptote is going to be wherever the numerator's number is. That's going to be the high point. And then it's going to go down from there because every time I divide by a number, my answer is going to get smaller, which means the maximum is the asymptote. So 105,000 people is your maximum. After how many years does the population reach 100,000? Well, I can put 100,000 in for P because P stands for population. So 100,000 equals 105,000 over 1 plus 2.7 e to the negative 0.0981 t. Well, I can put a 1 underneath the 100,000 and cross multiply. So I get 100,000 times 1 plus 2.7 e to the negative 0.0981 t equals 105,000. I can divide by 100,000, both sides. Divide by 100,000. So this leaves me with 1 plus 2.7 e to the negative 0.0981 t equals, and 105,000 divided by 100,000 is 21/20ths if I simplify it. Then I can subtract 1 from both sides. So 2.7 e to the negative 0.0981 t equals, and 21/20ths minus 1 is actually 1/20th. Then I can divide both sides by 2.7. And I get e to the negative 0.0981 t equals, and if I do 1/20th divided by 2.7 on my calculator, I get 1 over 54. Then to get rid of the exponent, I can take the natural log of both sides. So ln e negative 0.0981t equals ln of 154th. The left side, the ln e goes away, negative 0.0981t equals ln of 1 over 54. I can divide both sides by negative 0.0981, negative 0.0981, and I get a time of 41 years. So in 41 years, the population will be 100,000. All right, we have one more example. Archaeologists uncover an ancient wooden tool. They analyze the tool and find that it has 22% as much carbon-14 compared to the likely amount that it contained when it was made. Given that the half-life of carbon-14 is about 5,730 years and has K equal to 0.00012, about how old is the artifact? Round your answer to the nearest 100 years. Well, since we are decreasing in amount, we can use y equals ae to the negative kt. My y is how much is there in the end? Well, we know that it has 22% as much. So if the initial is a, then the after is 0.22a for 22%. My k is 0.00012, so negative 0.0012 t. So I can divide both sides by a. This gives me 0.22 equals e to the negative 0.00012 t. Got to get into the exponent, so take the natural log of both sides. Left side doesn't change, ln of 0.22. Right side, the ln and the e go away, negative 0.00012 t. Divide both sides by negative 0.00012. It says to round to the nearest 100 years. So when I divide, I get 12,617. So that means it's 12,600 years old. That's old. All right, kids, that's the end of 6.9. If you have any questions, please let me know. And as always, keep calm and keep trucking.